Hey guys, let's have a little chat about electricity, shall we? Electricity is all over the place. We use it in a jillion different ways, and so it's pretty important that we kind of have some kind of understanding of how this works. And I'd like to go to the next slide. Electricity it is the energy from charged particles. You remember that in the atom we have protons in the nucleus. Those are positive charges, and we have electrons in the outer shells of the atom, and those are negatively charged particles. And so there's a bunch of stuff that we do with particles, but that's what's making up the electricity here. Specifically, I'd like you to know that when you get two particles together, that they push on each other. Right here I have a picture of a negative charge and a second negative charge. You see how those repel? Those push away from each other. Meanwhile, if I have opposites, a negative and a positive, those would be attracted together. Anytime they're the same, there's a repulsion, whether they be negative or positive, like you see here at the bottom. But right there, you've got opposites, and those are going to attract. How hard do they pull or push on each other? Well, you've got Coulomb's law right here, which basically says we can work this out. We can calculate it, and you give me the two charges and how far apart they are, then I can tell you how much force they're going to have here. So let's do one of these real quick. We're interested in the force that this negative charge would be pulled to the right. That will be the same number that this force is pulled to the left with. And I'm going to make up some numbers here. Let's just say this is 1 Coulomb and this is 3 coulombs over here. Okay, now that is a positive and this is a negative. I don't usually put those signs into the formula simply because I already know that they're going to pull towards each other. So there's no big surprise there. But I got to go F equals K. K is this constant here. It's always the same number. Sometimes people like to pack that into the formula so they don't have to keep up with it. But you're going to have that number, 9 times 10 to the 9, Newton meter squared per Coulomb squared. Q1 would be the first charge. And again, I'm going to leave that negative sign out. Q2 is the second charge. Those are 1 Coulomb and 3 coulombs. So I just put those right here. And then I need to know the distance between them. The farther apart they get, then the weaker that force would be. This is what we call an inverse square law right there. Let's say they're 5 meters apart, shall we? So I'll put that number down here on the bottom. And don't forget to square it. That's the tricky part. So I need my calculator here, and that is right there. And I'm going to clear out all of this mess, and I'm going to just put that in just like it shows. Now that 9 times 10 to the 9, that's scientific notation, and the easiest way is with that EE right there. You see it's in yellow, so you got to hit the yellow button, the EE. Newer calculators, it's a blue button and blue EE, but same idea right there. I'm going to go 9 second EE, and then a 9. That's the 9. The E is the times 10 to the something, and this is the something. Then I can go times 1 times 3 and divide by 5. Don't forget the squared. Hit the square button right there, and you get a great big number. Okay, like I said, 1 Coulomb, 3 coulombs. Those are big, monstrous charges. So 108 with a whole bunch of zeros after it. Let's see how many. 1, 2, 3, 4, 5, 6, 7, right? So 3, 4, 5, 6, 7. I think I did that right. That's going to work out into newtons. What happens here on that is I have a Coulomb and a Coulomb here. That's going to make Coulomb squared, which will cancel this Coulomb squared on the bottom there. Similarly, I've got a meter which gets squared. That's going to cancel the meter squared on top. Nothing but newtons left there, which is good because we're looking for a force, and forces should be measured in newtons. So that looks well and good. All right, you could do that with any pair of charged particles. Now, this is about the electric field, which is similar to the electric force. We're kind of imagining that we're coming in here and we're putting in a small positive test charge. And you know that if I put a positive charge right there, that this positive and that positive would repel each other. They're like charges, so they repel, and I'm going to get a little push that way. And if I put it here, there'd be a push there. If I put it down here, there'd be a push this way. So this particle, the small positive test charge, is kind of an imaginary particle. It's not something that we're actually putting there. We're saying, if I put a particle there, what would the effect be? And so these lines right here radiating outward, that tells me that the electric field there is outward from a positive charge. And similarly, if I put a small positive test charge right here, little positive charge would be attracted and everything would go into the, or be attracted toward the negative particle there. So the sign of the charge determines which way the electric field points. Everything goes away from from a positive charge. Everything goes to a negative charge right there. You could have a whole bunch of charges, right? If I had a positive charge here and a negative charge over here, then when I put a small positive test charge here, it would be repelled by this guy and simultaneously attracted to the other guy. So I would get a field line that went across there. If I put it a little bit higher, it's going to be repelled from this guy, so it's going to start off this way, but eventually it's going to be attracted over to that one, and it's going to kind of arc that line like that. Down here, it'd be repelled by the positive charge, attracted, and so you get a series of lines that look kind of like that. All right. What if I had two positive charges like this? Everybody's trying to get away from both of those. So I'd get a field line out here and here and here. If I send one here, he's going to try to get away from this guy, and he's really close to that, so he's got a lot of drive to do that. But the closer he gets to this guy, he's going to be repelled by that too. And so it's going to kind of turn up, and it kind of does this weird thing right there where it kind of curves on this side. Everybody's trying to get away from both blue charges. Somebody here would come and be sent out. So you get this kind of weird thing. But basically all you're trying to do is think about how do I get away from both blue things? How do I get two red things? These should always have arrows on them indicating the direction. I neglected to do that up there, but let me add those in. And those are electric fields right there. Now we could calculate the magnitude of that as well. You don't really need to worry about that, but it's going to look like that, okay? It's the same thing that we had with electric force, but we don't have the second charge because we're not actually putting a charge. They're saying if I put a charge there, then it would go this way. All right, so we just take the Q right there, or I guess better right here, and we could find the strength of the electric field, and the direction would go like that. All right, don't worry about that too much, but that's kind of something that goes on there. We talk about the voltage, which is the strength of the electricity, how much oomph it has, how much push that it has. I've got some batteries up here in the picture. You can see this is one of those square 9-volt batteries. This is a C battery maybe, and a little AA or AAA there. I can't tell. It looks like a AAA. So those are different batteries. This guy has 9 volts. That tells me the voltage. That gives me the strength. This guy, an A battery, A, AA, AAA, a B, a C, a D, those are all 1.5 volts. They don't put it on there very often, but that's the voltage of that. These guys would be 1.5 volts as well. This is 6 times stronger than that. It will light up a light brighter. It will drive a motor faster. It will do more work. This comes back to how much potential energy, how much potential work it can do. So that's where we're we're going with these things. And the voltage is kind of the strength of the electricity. More voltage will get more done. All right. I have a idea here called current, and you can see that I've got a battery right here, and that battery is pushing current through this circuit. If I have a circuit, if I have a wire that goes all the way around from positive to negative, then I'll get this flow of electrons. Now the electrons actually come out of the negative terminal. This is my negative, my positive charges are up here. There's a chemical process going on that strips electrons off of there and sends them down here. Remember, those electrons don't like each other, so they repel each other. The protons are pretty much locked up in the nucleus of an atom, so they can't go anywhere, but these electrons can move, and when they do, they are repelled by this pole of the battery, and they are attracted around to the positive. So really what's going on is electrons are moving this way. However, somebody a long time ago, like Benjamin Franklin era, said, well, we know there's charged particles, and well, let's call one of them positive and the other one negative, and we don't know which way the current goes, but dadgummit, I'm going to define the current to go from positive to negative. So even though the electrons are really flowing the other way, they didn't know about electrons, and they guessed wrong. The current is defined to go from positive to negative. If it makes you feel any better, it's really electrons going from negative to positive, but either way that you want to think about it, that's what's happening right there. We measure that in amperes or amps, or you can just abbreviate it down to A. An amp is a coulomb per second. So remember, we said a coulomb was a whole lot of charge. If I count all the charges that are moving in this thing and divide by how long it takes for them to move, that gives me an amp of current. Okay? I have these things called resistors. These little guys right here are resistors, and they make it hard for the electricity to go through there. There's a wire that comes right here, then you've got the resistor and the wire over there taking it somewhere. This is part of the circuit, part of the current path. But these guys slow down the electricity. They oppose the flow of electricity. There's a lot of things that you can do with these and reasons that we would put them into a circuit, but anything that you open up, you're going to see a whole lot of these, and they're all over the place. We measure those in ohms, and because Mr. Ohm's name sounds like the Greek letter omega, we use this for the symbol for ohms. Something could be 47 ohms, right? And that would be the way we would write that out. An ohm is a volt per amp. We'll see more about that in just a little bit. But anything with resistance would be considered a resistor. Like if you had a motor in your circuit, if you had a light bulb, if you had a radio, a blender, any kind of thing that is using electricity, then that resists the flow of electrons and would be considered a resistor. Now, these guys down here, these are actual resistors. You can see that there's stripes on these. The stripes make up a code to tell you what kind of resistor that you have. And these are a little bit hard to read. The picture is not very clear. Let's go with this one right here. When I look at that, I see a brown stripe, a green stripe, and it looks like another brown stripe and a gold stripe. So there's 4 bands, and I want to put that gold last. Well, I can come over here to the chart and say I've got a brown and a green and then a second brown, and the gold means something else I'll tell you about in just a second. Let's take that brown, green, brown, and put those numbers down on the chart here. Brown is a 1, green is a 5, brown is a 1. And the way you do that is you take these first two and make it a number, and then you say times 10 to the third one right there, that 1 right there. Now that's a funny way to write numbers, but you can see here that 10 to the first power would be 10. 15 times 10 is 150, and so that would be a 150 ohm resistor right there. There's another example. If you had red, yellow, blue, you'd come over here and go 2, 4, 6. You put the first two numbers there. You take that third number, and it's the exponent on the times 10 to the something, right? And you put it right there. You can see that you can get anywhere from, 1 ohm up to millions and billions of ohms here with this thing. So it's a pretty handy code with only 3 digits, to be able to express that many numbers is pretty remarkable. That gold stripe that I mentioned on here, this guy, that is an accuracy band, and some resistors are 5% accurate. They're within 5% of what they say they are. Some are 2% resistors, 1% resistors, and so that just really tells you how good of a resistor it is. These things are super cheap, but the farther you go this way, the less accurate it has to be, then they're even cheaper. So industry likes to use the least accurate one that they can get away with, and usually that's fine, right? If you're doing super high-end, I don't know, military grade radios or something, would use low, probably even more accurate than that. But that's just a band to say, here's how good of a resistor it is. Okay. Now you could put a bunch of resistors together. You could put, if I didn't have all the resistors that I needed, I could add several of them together to get the value that I needed. And there's basically 2 ways that you can stack these things. Right here, I have resistors in series, and over here I have resistors in parallel. So let's talk a little bit about those. When they're in series, the current will flow through the first one, and then it flows through the second one, and then it flows through the third one. When they're in parallel, the current comes this way, and it has a decision to make. In the end, some of the current is going to go this way and out, and the rest of it is going to go the other way and out. So you see how the current splits right there, while the current here is go through the first one, go through the second one, and then go through the third one. All the currents going this way. So it behaves a little bit differently, and adding them in series or adding them in parallel is a good thing to be able to do here. You have to add them differently, of course. In series, you just add them up. If this is like, how much trouble do you have to go through, getting through school? I got to go through the first class, that's 100 hard. The second class is even harder, 300 hard, and the last one is 500. Well, you had to pass through 100 plus 300 plus 500. That's a total of 900 ohms of trouble there, right? And since these resistors cause trouble for the current, it's kind of the same thing, You go through all of them, you just add it up. On the other hand, over here, resistors in parallel, some of it's going this way and some of it's going that way. That makes it easier for all of the current to get through. It's kind of like if you were in a room and a fire broke out and everybody had to run through one door, there was only one way out. People would get jammed up and trampled and stuff, and it would be hard to get everybody out through one door. If you got 2 doors, if there are 2 paths that you can take, that makes it easier for everybody to get out. And the same thing happens here. This is what you have to do to add these. I've only got 2 here. This has got 3. How many ever resistors you have, you just keep going. That is the symbol for resistor, because you see how the electricity has to go to get through there, right? That little wiggle line, if you had a hallway that looked like that, it'd be hard to work your way through. So it's kind of the same thing here. If I wanted to add these 2, I could come down here and do it as a fraction. I could say 1 over R total equals 1 over the first one, which is 100 ohms, plus 1 over 300. And if I had more, I'd keep going, plus 1 over 500, whatever. I'd have to get a common denominator here. Common denominator would be 300. So I'd have 3 over 300 plus 1 over 300 is 4 over 300. And then I'd have to get a value for that. 4 divided by 300. And then there's one more thing that I'd have to do. See how that's 1 over R total? I'd have to invert the whole thing. I'd have to flip it on its head. That's what this button right here does. So I'd have 75 ohms of resistance with a 100 and a 300 in parallel. Remember how we said it made it easier? When I put resistors in parallel, that sum should be less than either one of the resistors that you have. Down here you see a little tricky way to do this by hand. I've got that 100 ohms, and remember that button that inverts things? I want to invert it right there. So if I go 100 inverse, then I want to add plus the next one inverted, so I could go 300 inverse. And that's all the resistors I have right there. So I'd hit enter. That gives me that upside down number. I still have to invert it one more time and get my 75. Okay? Here's one more of those real quick. If I had, no, not that. Where's the eraser? Is that the eraser? Maybe that's the eraser. Yeah, okay. Let me make a little bit of room right here, and I will create another one for you because I know you're enjoying this so much. Here is, let's do 3 in parallel this time. And I'm going to make this 10 ohms and 20 ohms and 40 ohms. Okay, remember how I said it should be, the answer to this should be less than any of them altogether. So I would guess we're somewhere around the 6 or 7 ohms would be the total on this. But let's find out real quick with the calculator. All I got to do is 10 inverse plus 20 inverse plus 40 inverse. Hit your enter and then invert it one more time. And 5.7 ohms would be the total resistance of that. Okay, so that's not too bad. And we've got the thing there. Now, here's what the electricity kind of does with the thing. And we're going to talk about this thing called Ohm's law right here. I kind of like it in this version, but the other version works fine too if you want to keep up with it that way. We talked about the voltage, how the voltage pushes the current through the circuit. We talked about the resistance, how the resistor fights that flow, restricts it. This is a cute little picture somebody made up. I don't know who or when. I just stole this off the internet. But you can see the voltage trying to push the current through this circuit, and the resistance up here is choking that down, so it's harder and harder for the current to go through. That's a pretty good way to think about it. But the Ohm's law here, this formula, is a mathematical way to think about it. And you've got the voltage, you've got the current, you've got the resistance, and the voltage is equal to the current times resistance. So that's a nice little math way to do that. I could come in here and let's say that the amp, the current is, I've got 3 amps, that's a good bit of electricity, and the resistance is 20 ohms. That's my R value. How strong would the voltage need to be to push 3 amps of current through a 20 ohm resistor? Easy peasy. You come in here and you say I equals 3 amps, and the resistance is 20 ohms, and 3 times 20 is 60, and the unit that should go on that would be volts. I need a 60 volt battery to make that happen. Okay, if I put a 50 volt battery, I wouldn't get as much current. Wonder how much I would get. Second problem here, if the voltage is only 50 volts and I still have that 20 ohm resistor, then I could come over here and use this version, or I could do a little bit of algebra. V equals IR. I want to solve this thing for I, so I need to get this guy by himself. That R is in the way, so I'm going to come up here and divide both sides by R. That'll cancel the R, leave that I by itself. And I'd have to do that voltage divided by the resistance. That's what it says over here too. So I've got the voltage, 50 volts. I've got the resistance, which is 20 ohms. And I divide, and that would be 2.5, I believe. 50 divided by 20, 2.5 amps. I wouldn't get 3 amps, I'd only get 2.5. Okay? A weaker battery means less current. A stronger resistor means less current. And all three of those are tied together. So that's kind of fundamental to understanding electricity and how it works and what's going on with the circuit. We talk about the power that something is using. There's two ways to think about it. It's the rate or speed that energy is used. So down here you have a picture of a light bulb. That light bulb is using electricity. You want to know how much electricity it's using? You can look right here on the top and it says 100 watts. And if you know that a watt is a joule per second, then you can see that that's a measurement of energy over a measurement of time. That's a speed of energy use, right? Now, somebody had to make that electricity, and so the other way to think about this is how much work do you have to do in order to generate that electricity. And down at the hydroelectric dam or at the nuclear plant or at the coal plant or whatever, they had to do 100 joules of work every second to make your light bulb go. And you multiply that out by, the whole city of Columbia, state of South Carolina, United States of America. That's a whole lot of work or energy that we go through every year. This watts is the unit. You see it on light bulbs and toasters and hair dryers and stuff. You can always turn it over and see what that number is and how much electricity, how fast it's using the electricity. That relates back to your electric bill, right? And they sell electricity in a unit called kilowatt hours. So if I ran a 100-watt light bulb for 24 hours, then that would equal 2,400 watt hours. And we want kilowatt hours, so I'd have to take this decimal place right here and move it 3 times, and I would have 2.4 kilowatt hours. All right? The power company is going to sell kilowatt hours, and it might be like, I don't know what it is here these days. Let's say it's 15 cents per kilowatt hour. Probably a little more than that now, I don't know. But I could come in here and go 2.4 times the 15 cents, and my electricity bill just went up 36 cents from running a 100-watt light bulb for 24 hours. All right, you run it all day, you forget and leave it on, that's not going to break the bank, right? A hair dryer is about 1,500 watts. Your stove is about 1,500. You leave that on for 10 hours, now we're talking 15,000 kilowatt hours or 15,000 watt hours, 15 kilowatt hours, and now you're about $2.25, that you're talking about. So don't go leaving this stuff on. I think I did that right. 15 times. Yeah, 15 cents would be 225. Move the decimal place. Yeah, $2.25 to leave your hairdryer running for 10 hours or something. So the electricity bill goes up, but we've had, cheap electricity for a long time. You think your electric bill is high, but really in terms of what you're getting, and what it takes to make that. We've had a cheap energy for 100 years or something. So anyway, here is the next thing. There are these devices called capacitors. The job of a capacitor is to store charge. It's a little bit like a battery in that it has charge in it, and then I can pull that off and use it when I want to. But these devices are all capacitors. These are variable capacitors. You can turn the crank here, and you see there are two little plates that here's a plate, and as you turn it, those are going to get closer or farther apart. Those plates are what store charge. So right here you can see there's a battery. This is the symbol for a battery, and it has a voltage. Battery, why does that look so weird? ERY, I think. The electrons are going to flow out of the battery when you hook this thing up, and they're going to come over here, and they're going to line up on this plate right here, and they are stored on that plate. Meanwhile, any electrons that are free here are going to escape. They're attracted to this positive terminal down here, so they're going to run around. That leaves positive on this plate because all these electrons left town. All right, I'm going to erase these because they went to the battery. These guys are stacked up here. I get positive on one side, negative on the other side. That charge is stored there. And then if I take away the circuit, take away all this right here, take away the battery, take away the wire. I can't erase the wire, it's in the picture. But that charge is still trapped there. So you can charge it up and you can leave it and save it for all sorts of practical purposes in electricity. Wanted you to know those exist. Lots of interesting things about those. You don't really need to worry about it. So that just wanted to show you the picture and how they work. There are two kinds of electricity here. One's called DC and one's called AC. Direct current is DC, and you can see right here that it's always putting out the same amount. If you've got a 9-volt battery and you graph the output of that, it's always 9 volts. It's direct, it's a straight line. So that's your DC power, direct current. Meanwhile, if you plug into the wall, that's AC, or alternating current. And you graph that, and it goes positive, negative, positive, negative, positive, negative. The electrons are actually moving back and forth in that wire. They go one direction, they go the other direction. But that sets up an electric field that is going to move and push your motor, light up your light bulb, run your radio, whatever you're doing. Okay, so those are interesting. That I could either have battery power that just always gives me the same amount, or I could have alternating current that alternates between positive and negative, between going to the right, going to the left. Okay, and I've got a couple devices here. This is a transformer, which is one way to change what's happening with the electricity. And basically the electricity is going to flow into this thing. There's a whole bunch of loops like you see right there. And when you pass electricity through a wire, it sets up a magnetic field. That magnetic field is going to come over here, pass through the other one, the other coil. There's two coils. And when you pass a magnetic field, changing magnetic field through a coil, you get a voltage, you get an induced current. And it's showing here that my original electricity was 120 volts AC. Well, I've got a bigger wave coming out here. I've got more voltage. So my output voltage can be calculated with that formula at the bottom of the page. We're going to call N1 the number of turns right here. So I'd go and I'd count 1, 2, 3. N1 equals 3. Meanwhile, N2 is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I think I did that right. N2 equals 9. So I know this number right here, and I know this number right here. We said the input voltage, that's the voltage on the first side, is going to be V1. I would like to find the voltage that comes out of that. If this is 120 volts AC, alternating current up and down, then how strong is it over here? And so I take my formula, N1, N2 equals V1 over V2, and I need to solve that for V2. Probably the easiest thing, it's just algebra, but probably the easiest thing is to cross multiply. So I'd end up with N1 V2 when I multiply that way, the bottom times the top on the other side. And then I want to multiply this way, that equals N2 V1. And since I'm trying to get this by itself, I need to get that V2 back where it started. So I'm going to divide both sides by V2, and I end up with that. I solved for the wrong one, I'm sorry. We want V2, so I need to divide by N1. There we go, on both sides. Okay, canceled out the wrong one. V2 equals N2, we said that was 9, times the voltage on side 1, on the primary side is what they call that. This is the primary, and this is the secondary coil. Okay, V1 was 120 volts, so I'd put that in right here. And then I'd divide by N1, this guy. On the primary I had 3 turns. And you can see that the number of turns cancels out. I'd have 9 divided by 3 is 3. 3 times 120 is 360. I started out with electricity 120 volts. I ended up with electricity at 360 volts. It got 3 times more voltage. I multiplied the voltage by a factor of 3 there. Okay, and the kind of short, quick way, if it works out, is you can take this number divided by that number and multiply your input voltage and get the output voltage there. It's that ratio of the number of turns on the primary and the secondary. Okay, I could also come out here and figure out what the current is going to be. Now they didn't give me a current here, so I'd have to make that up, but I can go ahead and tell you that you don't get anything for free, and that the power on this side, how fast this is using electricity, has got to be equal to the power on the other side. And back there we saw that power was current times voltage. So I could do a similar thing here. I've got 3 of the numbers. Let's say there's 4 amps on this side. Let's make it 6 amps. Okay, and so that's I1. This is 120. This is 360. See how I could solve that for I2? Just divide both sides by V2. I2 equals I1 V1 divided by V2. And I'm going to run out of space here, but I'm going to keep going anyway. I1 was 6 amps. V1 was my 120 volts. Down here, V2 is 360 volts. 120 goes into 363 times, so I'm really left with 6 amps over 3. The number of the volts canceled out. And 6 divided by 3 would be 2 amps. So I ran my voltage up by a factor of 3, but to make up for that, the current has to go down by a factor of 3. I multiplied voltage up, I divide by 3 to get the new current right there. I don't ever get anything for free. I'm just changing the electricity so that I have more voltage, but that means, you can't spread the same amount of electricity into a stronger electricity with the same current. It's got to come from somewhere. So one goes up and the other comes down like that. This formula kind of shows that. Look at the indices on this thing. I've got N1, number of turns on the primary, to number of turns on the secondary. I've got the voltage on the primary, voltage on the secondary. As the number of turns goes up, the voltage goes up, but the current's going to go the other way. See how these are flipped, I2 and I1? So that's pretty easy to keep straight. And you can even see if you did cross multiply here that you'd get I1V1 equals I2V2. That's that power on side 1 equals the power on side 2. So it's all kind of built in there, and that one formula takes care of everything with transformers. We can change electricity up, we can change it down. If you had an X-ray machine, then you want high voltage. So you'd have a transformer that looked like this, where there's a small number of coils and a big number of coils on the other side. And that would make a higher voltage. That would be a step-up transformer. Meanwhile, if you wanted a cell phone charger, you're plugging it into the wall, getting 120 volts, but your cell phone charger wants 7 volts. So I'd have to do it the other way. I'd have to have a whole bunch of coils on this side and then a few on this side, and that would step the electricity down with that same formula. There's only one formula you got to worry about there. Here's two other devices that are worth mentioning. We had the transformer which changed one alternating current to a different alternating current, or all within AC. Right here, I can also take alternating current and change it to direct current. I can take the outlet kind of electricity and change it into the battery kind of electricity. Okay? That's called a power supply. This is actually one out of a computer here, and you can go find scrap ones of these all over the place, because there's a whole bunch of scrap desktop computers that all over the place, old computers laying around. You can pull this out. You can get a whole bunch of different voltages off of this because there's a transformer in there, and they're stepping that voltage down from 120 down to, there's a 12 volt DC, there's a negative 12 volt DC, you've got a 5 volt and a 3.5 volt, I think, and seems like there's one more, but I don't remember what it is at the moment. So I put 120 volt in alternating current, and I get all of these DC currents out. That's a power supply. That's what your cell phone charger is doing also. Over here, I could also have an inverter. Some of you may have one of these. You plug it into the cigarette lighter in your car, which is essentially a battery type electricity. You're using the battery of your car, and you're making alternating current with it. And you can plug your laptop in when you're on a trip or something, and keep things going. All right, so those are useful to know about too. You could buy either one of those. These are actually probably easier to buy. You could go to a big box store and into the car parts section and find one of those. Here, go find an old computer and start taking it apart, and don't shock yourself, okay? Now, last thing I wanted to talk about was, where do we get this electricity from? We get it from the power plant, but there's a whole lot of different kinds of power plants, and so I put some of them up here at the top and wanted to talk real quick about how our electricity gets made. We can burn coal, and when you do that, you're going to burn the coal. That gets hot. We're going to put that heat into water, and basically we are boiling water, which makes steam, and then we're going to run the steam through a generator. Here's a picture of a steam generator right here. So basically you're blowing the steam into the generator, and you've got these fan blades, and the steam is going to turn those fan blades. And then over here you've got a whole bunch of magnets and some coils, and you're turning those you're either turning the magnets around the coils or the coils around the magnets, depending on which way it's made. But remember, we said that if you have a changing magnetic field in a coil, that it makes a voltage. That voltage is then going to be sent out over the power lines. Right here's a transformer. So they're sending high voltage electricity from the power plant. They step that down to 120 volts or 240, I guess, and then it goes into your house, and you can use it. And those wires, those things go all over the country, and we've got the power grid that supplies electricity everywhere. Okay, if a transformer blows up, then you don't get power, right? If if somebody hits a power pole right here with their car, knocks the power line down and the wires break, you're not going to get power, right? But the grid is pretty strong, and there's secondary routes for everything to go, so most things are backed up somewhere. It shouldn't be too bad. Here's a second option. I could have a wind turbine up in the sky. As the wind blows past this thing, it makes the fan blade turn, which is the same thing that you have right here. The generator is built in right there at the top of every one of these things. So every one of these poles you stick up, if you drive out west, you see a whole bunch of these because there's lots of open space and there's lots of wind, and they just sit there and spin all day and make electricity. We have to pay for the pole and putting it up. There's some other problems. Birds run into them, but everything comes at a cost, and we have to, you have to recycle the fan blades every so often or whatever. It has problems too, but this is a renewable energy. Coal is not renewable. We're going to run out of coal one day. And when there's no more coal, then we won't be making electricity in coal plants anymore. There's some other problems with coal. They've got the smokestack here where they're burning all that coal, and for decades, for maybe 100 years, we just pumped out a whole lot of coal smoke without any real consideration for what it was doing. Well, what it was doing was poisoning the planet and polluting the atmosphere and changing the thermal blanket around the earth so that we picked up more heat, and so there's a lot of problems here. Now, with coal plants today, they put in these little filters that pull most of the soot and the smoke and the bad chemicals out, so it's not quite as bad as it used to be. But there's no such thing as clean coal. Coal is pretty nasty. I used to do blacksmith work, and you build a little coal fire and put your metal in it and beat on it, and then you'd blow your nose for the next 3 or 4 days, and it would come out black. It's just nasty stuff. There's no way to make it completely clean, but we can make it cleaner. Add that to the fact that eventually it will go away. There won't be any more of it. We've dug it all up that we can get to, and so that's not a renewable source of energy. Wind energy is. We're always going to have the wind. Uranium is another way. We could have a fission nuclear plant here, and there's one up north of Columbia, for example, Jenkinsville, and there's several others in the state. They are using uranium, which is radioactive, and so you've got these atoms of uranium in there, and neutrons come out, and they'll break this atom into something else, and that releases more neutrons, and so you get a whole lot of energy released right there. Again, all we're doing with it is boiling water, making steam, and turning a steam turbine. So that's a pretty high, fancy way to do that. We get a lot of energy out of this process. So nuclear power has been a pretty good option. You have to be very careful with it, because if an accident happens, then you've got all this energy going around and making people sick. In this country, we've been pretty good about maintaining safety, and we have a system to check and regulate everything. And there have been a couple little things, 3 Mile Island, if you want to look into some of that. But in other countries, they've had incidents like Chernobyl, where the whole thing just melted down, and they've got this radioactive wasteland that people 40 years later still can't live in. So there's some problems with uranium, with nuclear plants. Right here is petroleum. We can pump oil up out of the ground. We can burn it. We can boil water. We can make steam. We can turn a turbine. Okay, so that's kind of the same old thing. Again, not renewable. Uranium, not renewable. Hydropower here, Lake Murray is full of water, and when you let that water fall through a turbine, I'll put some little fan blades on it here, if I ran water through there, that would turn my turbine, which would turn the generator, which would make electricity, which would send electricity to your house. So we use a whole lot of hydropower in this country and all around the world. That's a good source. Now, it does take a whole lake full of water there to hold and do stuff, but then people get to use their boats and stuff, and there are other problems, other issues, other benefits, but that's a pretty good source. Solar energy is renewable. I guess hydropower would be considered renewable. Natural gas, I could burn natural gas, same old deal, boil water, make steam, turn turbine, right? But at some point we kind of run out of there. We do know how to make biomass. We do know how to make gas out of corn and any kind of plant material. When it decomposes, will make methane and other gases that we can use. So that's kind of renewable. Cars use a little bit of corn energy in them, and Brazil has run solely on corn, well, not corn, but biomass for, I don't know, 40 years maybe, something. So they're way ahead of us in that game. The solar is interesting. You make a little panel, sunlight comes down, and it's got enough energy to make electrons jump from one side to another, and that makes them flow, and that flow of electrons is a current. So solar energy is free for the taking. We do have to build the panels, install the panels, but it's a whole lot cheaper and a whole lot more efficient than it used to be. And that will be a big part of our energy for the future. Down here at the bottom, excuse me, I've got a graph from 1950 up to 2020 that shows what kind of energy where we were getting our energy, right? This beige line that was on top is coal. So you can see that that's been the predominant source of power for a long time in the U.S. Right now, it's down to about 19%. But right around nuclear's 20%, renewables are 21%. Again, that would be the wind and the hydropower and the solar are about a fifth of everything. Natural gas is about 40%. Right there, you can see that that's been going up over the time. So we found more ways to use that. Additionally, it's super cheap, super easy to build a natural gas plant, and so that's kind of a benefit there. Nuclear, the red line there was down pretty low, but in the 1970s we got busy and started making that, and then it tapered off. We haven't made any new nuclear plants in a long time. We started the one up of, building a new reactor up at Jenkinsville, and the scoundrel politicians took off with all the money, and so it never got finished. And similar things around other parts of the country. But, we need to make some hard decisions about energy and how we're using it and what we're using it for and how we're going to get it. This will be an interesting question for centuries to come. So that's a little bit about electricity, and we'll talk about this in class. Bring any questions you have. Work the questions in the LOP, and I'll catch you next time. Thanks. Have a great day.